NEC 220.3B pertains to branch circuit supplying motors. It requires a minimum ampacity of 1.25 times the full load current rating of the motor. Example donut applies this 1.25 factor to the motor load when calculating the service ampacity. However, the example is not meant to imply that this factor applies to service calculations in general. NEC 220.3B is not applicable to service calculations. Service ampacity is determined by the requirements of NEC 220.4T, which do not include a 1.25 factor for motor loads. The reason for this is that service calculations are intended to provide the minimum capacity necessary to supply the entire electrical load of the facility, including both continuous and non-continuous loads. Motor loads are typically non-continuous, and they are usually not running at full load for extended periods. Therefore, it is correct not to add the 1.25 factor to motor loads when calculating service ampacity. The 1.25 factor only applies to branch circuit supplying motors, as specified in NEC 220.3B3. When calculating service ampacity, it's crucial to distinguish between branch circuit requirements and overall service load calculations. Branch circuits, as covered by NEC 220.3B3, necessitate the 1.25 factor for motor loads to account for the potential of continuous operation at or near full load, as well as to provide a safety margin for motor starting currents. However, service ampacity calculations, guided by NEC 220.40, take a broader view, considering the entire facility's load profile, encompassing both continuous and non-continuous loads. Since motor loads are often non-continuous and not constantly running at full capacity, applying the 1.25 factor across the board to service calculations would lead to an overestimation of the required service size. This overestimation can result in unnecessary expenses related to equipment and installation. The NEC structure is designed to ensure that each section addresses specific aspects of electrical installation. Section 220.3 focuses on branch circuit calculations, while Section 220.40 deals with service load calculations. This separation is intentional to allow for tailored approaches based on the nature of the electrical load. For branch circuits feeding motors, the 1.25 factor is vital to prevent overheating and ensure reliable operation. For service calculations, a more holistic assessment is needed, considering the diversity of loads and their duty cycles. Example donut in the NEC can sometimes cause confusion because it applies the 1.25 factor to a motor load within a service calculation. However, it is important to understand that this example serves a specific purpose, demonstrating how motor loads are considered within the overall service calculation framework. It does not mean that the 1.25 factor should be universally applied to all motor loads in service calculations. To accurately calculate service ampacity, firstly determine the total continuous load. Continuous loads are defined as loads that operate for 3 hours or more at a time. These loads must be calculated at 125% of their maximum current demand. Secondly, calculate the non-continuous loads. These are loads that operate for less than 3 hours at a time. Calculate these loads at 100% of their maximum current demand. Thirdly, add the continuous and non-continuous loads together to determine the total calculated load. Fourthly, ensure that the service has adequate capacity for the calculated load, plus any future load growth. Consider factors such as the facility's expansion plans and potential increases in electrical demand. Fifthly, refer to the appropriate NEC tables to determine the minimum allowable ampacity for the service conductors, based on the calculated load and the type of conductors used. Factors like ambient temperature and conductor bundling may require adjustments to the ampacity ratings. In summary, applying the 1.25 factor to motor loads is appropriate for branch circuit calculations, ensuring safe and reliable motor operation. However, for service ampacity calculations, a broader perspective is necessary, considering the diversity of loads and their duty cycles. Following the guidelines in NEC 220.3B and carefully assessing the facility's load profile will result in an accurate and cost-effective service ampacity calculation. The NEC provides detailed guidelines for calculating electrical loads to ensure safety and prevent overloading of electrical systems. For service ampacity calculations, it's crucial to follow the specific requirements outlined in Article 220, particularly Part Roman III, which covers general requirements for calculating feeder and service loads. The general approach to calculating service ampacity involves several steps. Firstly, determine the total connected load. This includes all electrical loads in the building or facility, such as lighting, receptacles, appliances, HVAC equipment, and motors. Secondly, apply demand factors to the connected load. Demand factors are multipliers that reduce the calculated load based on the likelihood that not all loads will be operating at their maximum demand simultaneously. Demand factors vary depending on the type of load and the occupancy of the building. Thirdly, calculate the feeder and service loads. This involves summing up the individual loads taking into account any applicable demand factors. Fourthly, determine the minimum service ampacity. The service ampacity must be sufficient to supply the calculated feeder and service loads, as well as any future load growth. The NEC provides tables and guidelines for determining the minimum ampacity of service conductors and overcurrent protection devices. For motor loads, the NEC provides specific requirements for calculating branch circuit feeder and service loads. For branch circuits supplying motors, the ampacity of the conductors must be at least 125% of the motor's full load current rating, as specified in NEC 430.22. This requirement is intended to account for the motor's starting current, which can be several times its full load current. For feeders and services supplying motors, the NEC provides demand factors that can be applied to the motor loads. These demand factors recognize that not all motors will be operating at their full load current simultaneously. The demand factors vary depending on the number of motors and their operating characteristics. In addition to the general requirements and the motor-specific requirements, the NEC also provides specific rules for calculating the loads of certain types of equipment, such as HVAC equipment, electric ranges, and data processing equipment. These rules are intended to ensure that the calculations accurately reflect the actual loads of these types of equipment. When calculating service ampacity, it's important to consider all applicable requirements of the NEC, including the general requirements, the motor-specific requirements, and the equipment-specific rules. Following these requirements will help ensure that the electrical system is safe and reliable. NEC 220.3 addresses general requirements for branch circuit, feeder, and service calculations. The specific part, 220.3B, which you mentioned, deals with the calculation of branch circuit loads. It's important to note that while the principles outlined in 220.3 can inform the overall approach to electrical load calculation, the direct application of the 1.25 factor from 220.3B3 to service ampacity calculations is not universally required or appropriate. Example donor found in Annex D of the NEC provides examples of how to calculate feeder and service loads for various types of occupancies. While these examples are helpful for understanding the application of the NEC requirements, they are not mandatory rules. The specific example you referenced might include the 1.25 factor for motor loads in the service calculation for illustrative purposes, but it doesn't mean that this factor must always be applied in all service calculations involving motors. The decision of whether or not to include the 1.25 factor for motor loads in service calculations depends on several factors. Firstly, the type of motor load. If the motor load is considered continuous, meaning it operates for 3 hours or more at a time, then it's generally appropriate to include the 1.25 factor. This is because continuous loads are more likely to draw their maximum current for extended periods, and the 1.25 factor provides a safety margin to prevent overloading. Secondly, the diversity of the motor loads. If there are multiple motor loads, and they are not all expected to operate simultaneously at their full load current, then it may be possible to apply demand factors to reduce the calculated load. Demand factors are multipliers that reflect the likelihood that not all loads will be operating at their maximum demand at the same time. Thirdly, the specific requirements of the local electrical code. Some local jurisdictions may have specific rules or interpretations regarding the application of the 1.25 factor for motor loads in service calculations. It's always a good idea to check with the local authorities to ensure compliance with all applicable regulations. In general, it's best to err on the side of caution when calculating service ampacity. If there's any doubt about whether or not to include the 1.25 factor for motor loads, it's generally safer to include it. This will ensure that the service has adequate capacity to handle the maximum potential load, even if it's unlikely to occur. However, it's also important to avoid oversizing the service unnecessarily. An oversized service can be more expensive to install and maintain, and it can also lead to lower efficiency. The goal is to strike a balance between safety and cost-effectiveness. To make an informed decision about whether or not to include the 1.25 factor for motor loads in service calculations, it's essential to carefully consider all of the relevant factors, including the type of motor load, the diversity of the motor loads, and the specific requirements of the local electrical code. It's also a good idea to consult with a qualified electrical engineer or contractor to get their professional opinion. They can help you assess the specific circumstances of your installation and make the best decision for your situation. Remember that the NEC is a complex and evolving document. It's important to stay up to date on the latest changes and interpretations to ensure that your electrical installations are safe and compliant. Consider attending training courses, reading industry publications, and participating in online forums to expand your knowledge and stay informed about the latest developments in the electrical industry. In the context of calculating service ampacity, understanding the differences between continuous and non-continuous loads is very important. Continuous loads are defined as those that operate for 3 hours or more at a time. Examples include lighting in commercial buildings, HVAC systems, and industrial machinery. Non-continuous loads are those that operate for less than 3 hours at a time. Examples include household appliances, power tools, and intermittent use equipment. The NEC requires that continuous loads be calculated at 125% of their maximum current demand. This is because continuous loads are more likely to draw their maximum current for extended periods, which can lead to overheating and equipment failure. Non-continuous loads, on the other hand, can be calculated at 100% of the maximum current demand, as they are less likely to operate at the maximum demand for extended periods. When calculating service ampacity, it's important to identify all continuous loads and apply the 125% factor to their current demand. This will ensure that the service has adequate capacity to handle the continuous loads without overloading. It's also important to consider the diversity of the loads. Diversity refers to the likelihood that not all loads will be operating at their maximum demand simultaneously. If there are multiple loads, and they are not all expected to operate at their maximum demand at the same time, then it may be possible to apply demand factors to reduce the calculated load. Demand factors are multipliers that reflect the likelihood that not all loads will be operating at their maximum demand at the same time. The NEC provides tables of demand factors for various types of occupancies and loads. When applying demand factors, it's important to be conservative and avoid oversizing the service unnecessarily. An oversized service can be more expensive to install and maintain, and it can also lead to lower efficiency. The goal is to strike a balance between safety and cost effectiveness. The NEC provides guidelines for calculating the ampacity of conductors based on their size, insulation type, and installation method. It's important to select conductors that are adequately sized for the calculated load and the environmental conditions in which they will be installed. The NEC also provides guidelines for selecting overcurrent protection devices such as circuit breakers and fuses. Overcurrent protection devices are designed to protect conductors from overheating and damage due to overloads and short circuits. It's important to select overcurrent protection devices that are appropriately sized for the conductors they are protecting and the equipment they are supplying. In addition to the NEC, there may be local electrical codes and regulations that apply to service ampacity calculations. It's important to check with the local authorities to ensure compliance with all applicable regulations. Local codes may have specific requirements for certain types of occupancies or loads, or they may have stricter requirements than the NEC. Staying informed about the latest changes and interpretations of the NEC and local electrical codes is crucial for ensuring the safety and compliance of electrical installations. The NEC is updated every 3 years, and local codes may be updated more frequently. Consider attending training courses, reading industry publications, and participating in online forums to expand your knowledge and stay informed about the latest developments in the electrical industry. In summary, calculating service ampacity is a complex process that requires careful consideration of all applicable factors. It's important to follow the guidelines in the NEC, apply demand factors appropriately, select adequately sized conductors and overcurrent protection devices, and comply with all applicable local codes and regulations. Consulting with a qualified electrical engineer or contractor can help ensure that the service ampacity calculation is accurate and that the electrical installation is safe and compliant.